As the wheel turns at a constant speed, the shadow of the peg sweeps back and forth on the surface beneath. Notice that the spot moves fastest near the center of its sweep and slows to a stop at the ends of its sweep. The center is the spot's equilibrium position. The movement of this spot is an example of simple harmonic motion. The spot gains speed fastest as it begins its trip from a side. In other words, its acceleration is greatest at the extremes. Approaching the middle, its speed is fastest, but its acceleration has dropped to 0. As the spot crosses the middle, the acceleration reverses direction and increases to its maximum magnitude as the spot reaches the other end. Simple harmonic motion occurs when the motion's acceleration is directed toward the equilibrium position and when the acceleration is stronger with increased distance from the equilibrium position. In simple harmonic motion, acceleration is proportional to distance from the equilibrium point. We are going to derive an equation that relates the position of the spot on the x-axis to the angular velocity of the peg omega on the rotating wheel and the time t. From the diagram, you can see that cosine theta equals x divided by a. Thus, x equals a times cosine theta. From your study of circular motion, you'll remember that theta equals omega times t. So, now the equation can be written. X equals a times cosine omega t. A is the amplitude. It represents the greatest distance on either side of equilibrium that the spot reaches. This question involves using the equation x equals a cosine omega t, which we just derived in the previous frame. The amplitude of the moving spot is 5.0 meters. The peg is moving around the center at a constant rate of 1.5 radians per second. Where is the spot 2.5 seconds after it leaves the positive x-axis? Which choice is the correct answer? Try using the formula for position. X equals a cosine omega t. Correct. Study the solution to the question carefully. Now try the next question. Here is a question. The amplitude of the spot is 5.0 meters. The peg is rotating around the center at a constant rate of 1.5 radians per second. How long would it take for the spot to travel all the way from the far right side to the far left side? Pick one of these choices after you have tried to solve the problem. Here are 3 hints. Correct. Study the solution to the question carefully. In the first question, the position of the spot at 2.5 seconds after starting was negative 4.1 meters. Do you suppose the spot in the first question was moving to the left or to the right after 2.5 seconds? Incorrect. Correct answer, to the right. At 2.1 seconds, the spot has stopped moving momentarily. If we locate the spot at 2.5 seconds, as we did in the previous question, then the spot is moving to the right, back toward the equilibrium. Velocity of the peg as it moves around the circle is drawn tangentially from the position of the peg. The peg is moving at a constant velocity v equals omega r equals omega a. Notice that theta 1 equals theta 2 equals theta 3. Now, sine theta 3 equals minus the velocity along x, v sub x, divided by the velocity along the wheel, v. And so, v sub x equals minus v times sine theta 1. By using omega a equals v and theta equals omega t, the equation becomes v sub x equals minus omega A times sine of omega t. Try this question. What is the velocity of the spot 1.0 seconds after it has started at its maximum amplitude on the right if the amplitude is 4.8 meters and the wheel rotates at 2.0 radians per second? Pick one of these choices after you have tried to solve it. Use the velocity formula. Correct. So, the spot on the x-axis is moving at 8.7 meters per second to the left. As the drawing indicates, the position of the spot after 1.0 seconds is at x equals negative 2.0 meters. You may wish to verify this position. Remember that to verify the position, you'll want to use the equation x equals omega A times cosine omega t. We have equations for position, x, and velocity, v. The third thing we need to do is to derive an equation for the acceleration, a, of the spot. For this derivation, recall that centripetal acceleration, a sub c, equals v squared divided by r, and since v equals omega r, then v squared divided by r equals omega squared times r squared divided by r. So, the centripetal acceleration is omega squared times r, or a sub c equals omega squared times a. As the peg moves at a constant velocity to the top of the circle, the spot on the x-axis accelerates. Cosine theta equals negative a sub x divided by a sub c, and a sub x equals negative a sub c cosine theta, or a sub x equals negative a sub c cosine omega t. Since the centripetal acceleration a sub c equals omega squared times a, the acceleration of the spot along the x-axis, a sub x, equals negative omega squared times a cosine omega t. Try this question. What is the acceleration of the spot on the x-axis at t equals 1.2 seconds? The amplitude is 3.0 meters, and the angular velocity, omega, is 0.75 radians per second. Pick one of these choices. Correct. Please check your work against this. Notice in the sketch that the spot is 1.9 meters from the equilibrium point. How would you have known that the spot is at that point? The position 1.9 meters was obtained by using the equation x equals a cosine omega t. After putting in the numbers for the amplitude, the angular velocity, and the time, you have x equals 3 times cosine of 0.75 times 1.2, which equals 1.9 meters. Here are the three formulas that describe position, velocity, and acceleration of an oscillator. Position, x, equals a times cosine omega t. Velocity, v, equals negative omega times a times sine omega t. Acceleration, a, equals negative omega squared times a times cosine omega t. The time that it takes for the peg to make a complete circle is called the period. The units of the period are seconds per cycle. Frequency f is the number of cycles per unit of time. The frequency is the inverse of period. The SI unit of frequency is the hertz, where 1 hertz equals 1 cycle per second. Also, watch the spot going back and forth on the flat surface under the light. The period is also the time that it takes for the spot to make a complete cycle. Remember from kinematics that distance equals velocity times time? Here, we use circumference, c, equals velocity times time, where the velocity of the peg as it moves around the circle is v equals omega r, and c equals 2 pi r. The time, t, for one period is t. T can be written as t equals 2 pi divided by omega. What you're looking at is one way of seeing that after moving through 1/4 of a period, you have gone pi over 2 radians, or 90 degrees around the circle. Theta is the measure of the angle in radians counterclockwise around the circle, starting at the positive x-axis. Theta equals omega t. 1/4 of a circle is covered in 1/4 of the time. It makes sense. The time, t, in seconds, corresponds to the position, pi over 2, in radians. Where would the peg be if it traveled around the circle for half the total period, 1/2 t? Answer: 1/2 t would be the time required to travel around 1/2 a circle, 180 degrees, or pi radians. Take a moment to figure out how many radians around the circle you would travel in 3/4 t and in t. In 3/4 of the time, 3/4 t, the spot will move 3 pi over 2 radians. To go the full circle takes the full period, t, and in that time, the peg moves 2 pi radians. Let's go around the circle one more time, only this time we'll concentrate on the spot moving back and forth on the surface below the circle. Here, the position is x equals a. The velocity is 0, and the acceleration is at its maximum. The maximum acceleration, negative omega squared times a, is negative in this case because it is directed to the left. Here, the position of the spot is x equals 0. 1/4 of the period has elapsed, t over 4. The velocity of the spot on the surface below the rotating circle is at its maximum at this position. Notice that sine of omega t equals sine theta equals sine of pi over 2 equals 1, which is the maximum value of the sine of an angle. At this position, the acceleration of the spot is 0. This is clear from the fact that cosine of omega t equals cosine of theta equals cosine of pi over 2 equals 0. Here, the position of the spot is at x equals negative a. 1/2 of the period, t over 2, has elapsed. The velocity of the spot is again 0. The acceleration of the spot is at its maximum toward the right of this position. Here, the position of the spot is x equals 0. 3/4 of the period, 3t over 4, has elapsed. The velocity of the spot is at its maximum. The acceleration of the spot is now 0. The spot has now completed a cycle. It has moved from positive a through 0 to negative a, and has moved back through 0 and ended back at positive a where it started. This is one complete period, or one cycle. The time elapsed is t. You might wish to verify that v equals 0 and a equals negative omega squared times a. As the circle rotates at a constant speed, omega, the spot on the moving surface traces a sinusoidal curve. Given the information in the preceding frames, you should be able to draw a graph of position versus time for an oscillating object. Try this before you advance to the next frame. This graph shows the position of the spot moving back and forth in completing one cycle. Note especially the positions at t over 4, t over 2, 3t over 4, and t. At t over 4 and 3t over 4, the spot crosses the equilibrium point. Here is the velocity of the spot as it sweeps back and forth. Notice that at positions t over 4 and 3t over 4, the spot crosses the equilibrium points and has its greatest velocity. Here is the acceleration of the spot as it sweeps back and forth. Simple harmonic motion occurs when the acceleration is directed toward the equilibrium position and is proportional to the distance from the equilibrium point. Notice that the maximum acceleration occurs when the spot is at its maximum amplitude. And notice that the acceleration is directed toward the center. Try this problem. An oscillating object is behaving according to this equation. X equals 3.0 meters times cosine of pi over 2 times t. Find the amplitude, period, and frequency of the object's motion. Comparing this equation with the standard equation gives you the amplitude and the angular velocity. The period t is found using the angular velocity, and then the frequency is gotten from the period.